As we begin our vast journey beyond the familiar confines of our solar system, it's essential to first understand where the reach of our sun begins to fade. A cosmic border not marked by visible lines, but by invisible forces and boundaries, where a familiar environment gives way to the unknown. This is the edge of our solar system, a region where the sun's influence diminishes and the vastness of interstellar space beckons. When we picture the solar system, most of us imagine the 8 planets circling the sun: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, each nestled within their orbits, bathed in the sun's light and warmth. Yet the solar system extends far beyond these planets. It is enveloped in a vast bubble of charged particles and magnetic fields that emanate from the sun itself, creating what scientists call the heliosphere. This heliosphere acts as a protective shield against cosmic radiation and interstellar matter, stretching out for billions of kilometers into space. To truly appreciate the boundary between our solar neighborhood and the rest of the galaxy, we must explore this invisible sphere and understand its complex layers. The sun is not only a luminous orb lighting our days, but also an active star continuously emitting a continuous stream of charged particles known as the solar wind. This solar wind streams outward at speeds of hundreds of kilometers per second, sweeping through the solar system, sculpting magnetic fields and pushing against the tenuous gas and dust that exist in space. As the solar wind radiates outward, it interacts with and ultimately competes against the incoming flow of particles and magnetic fields originating from beyond our solar system, the interstellar medium. The pressure of these two opposing forces defines the limits of the sun's domain. Close to the sun, the solar wind travels freely through space, expanding rapidly, undeterred by external forces. But as it journeys outward, it gradually loses speed and energy. Eventually, it hits what is called the termination shock, an invisible boundary where the solar wind slows abruptly from supersonic speeds to subsonic speeds due to its collision with the outer reaches of the heliosphere. This is not a hard physical boundary, but rather a turbulent and dynamic region that marks the first major slowdown in the solar wind's journey. Beyond this lies the heliosheath, a vast and turbulent zone where the slowed solar wind is compressed and heated as it pushes outward and resists the encroaching interstellar medium. This chaotic region is a transition zone, a kind of cosmic buffer where particles swirl, magnetic fields tangle, and the environment becomes increasingly complex. It extends until the solar wind is finally balanced by the external pressure of interstellar space. The final frontier of the sun's influence is a boundary known as the heliopause. This is where the outward push of the solar wind stops completely, as the forces from the interstellar medium balance the pressures from our solar wind. Crossing this boundary means leaving behind the protective bubble shaped by our sun and entering the uncharted, raw environment of interstellar space. It is a threshold marking the edge of our solar system, not by physical walls, but by changes in the nature of space itself, from a star's dominion to the vast, mysterious depths between the stars. Understanding these boundaries isn't just a matter of curiosity. They help scientists grasp how our solar system interacts with the rest of the Milky Way galaxy. This interaction affects everything from how cosmic rays, energetic particles from distant sources, can penetrate into the inner solar system, possibly influencing planetary atmospheres and even conditions for life. The sun's magnetic bubble also acts as a shield against harmful extragalactic particles, adding an unseen layer of protection to our delicate planetary system. It's remarkable to consider that despite the apparent emptiness of space, there is a continuous push and pull, a delicate dance of energies at the edge of our solar system. The boundary is not fixed. It fluctuates with the sun's activity, expanding and contracting like a cosmic heartbeat. During periods of intense solar activity, the solar wind grows stronger, pushing the heliosphere further out. Conversely, during quieter times, the heliosphere can contract, allowing more interstellar material to come closer. Our understanding of this cosmic frontier significantly advanced with the ingenuity of human curiosity and technology. Specifically, with the launch of the Voyager spacecraft in the late 1970s, these trailblazing probes have journeyed through the solar system, crossed the termination shock and heliosheath, and moved beyond the heliopause, becoming humanity's first emissaries into interstellar space. Their data provides a direct glimpse into this mysterious borderland, revealing the complex and dynamic nature of the sun's fading influence. In this vast expanse, where the familiar fades and the alien begins, we stand at the threshold of cosmic frontiers. The edge of our solar system is a place of transition, a veil behind which lie the infinite possibilities and mysteries of the galaxy. It is a reminder that our place in the universe is both grand and humble, a tiny star's domain giving way to the vast reaches of interstellar space awaiting discovery. As we embark on the chapters ahead, we will delve deeper into this boundary and beyond, tracing the path of our robotic pioneers, investigating the nature of the space between stars, and exploring the stellar neighbors that join our sun in the tapestry of the Milky Way. Each step will bring us closer to understanding not just the limits of our solar system, but the boundless cosmos that lay beyond, inviting us to explore what truly lies beyond the stars. Now, with this primer on the edge of the solar system, our journey begins. Let us turn our gaze outward and onward to the heliopause, the real boundary of the solar system, where the sun's influence wanes and the mysteries of interstellar space await. Beyond the planets and the farthest edges of the sun's magnetic grasp lies a crucial boundary, a threshold that separates our solar system from the vast expanse of the interstellar medium. This boundary is known as the heliopause, and it serves as the true frontier where the sun's influence effectively ends and the realm of the galaxy begins. To understand the heliopause, we start by looking at the nature of the solar wind, a fierce, continuous flow of charged particles, mainly protons and electrons, emitted by the sun's hot outer atmosphere. This solar wind streams outward in all directions, creating a protective bubble around our solar system called the heliosphere. The heliosphere extends for several billion kilometers beyond the orbit of Neptune, shaping the environment through which both photons and charged particles travel. As this solar wind expands, it eventually confronts the interstellar medium, the material that exists in the space between stars, which itself is a mixture of gas, dust, cosmic rays, and magnetic fields originating from other stars and galactic processes. Here begins a cosmic confrontation between the outward pressure of the solar wind and the inward pressure of the interstellar medium. The heliopause is the physical location where these two opposing forces reach equilibrium. Beyond this boundary, the interstellar medium's particles and magnetic fields dominate, pushing back against the solar wind so effectively that the sun's charged particles can no longer extend beyond. In essence, the heliopause acts like a cosmic shoreline, where the solar wind sea meets the vast ocean of interstellar space. Why is this boundary so important? For one, it defines the limits of our sun's protective bubble, guarding the planets inside from high-energy cosmic rays and other particles that travel across our galaxy. The heliosphere and its boundary help shield Earth from a hostile cosmic environment that could otherwise strip away atmospheres or bombard surfaces with dangerous radiation. The location of the heliopause is not fixed. It changes in response to both the solar wind's intensity and the density or pressure of the interstellar medium. During periods of heightened solar activity, such as solar maximum, when the sun's magnetic fields and particle emissions peak, the heliosphere grows larger, pushing the heliopause outward. Conversely, during quieter phases, it contracts inward. This dynamic interplay means the boundary is a fluctuating, ever-shifting frontier, rather than a static wall. Physically, the heliopause exists roughly between 120 and 150 astronomical units, AU, from the Sun. 1 AU being the average distance between the Earth and the Sun, about 150 million kilometers. For perspective, Neptune lies about 30 AU from the Sun, much closer, within the solar wind's relatively gentle breeze, underscoring just how far this boundary extends into space. Spacecraft missions, particularly the Voyager 1 and Voyager 2 probes, have provided the only direct measurements ever made of the heliopause. Voyager 1 crossed the heliopause in August 2012, and Voyager 2 followed in November 2018, providing groundbreaking data about conditions at this extreme boundary. These spacecraft revealed a sudden increase in cosmic ray intensity, a sign that they had left the Sun's particle-dominated region and entered the galactic environment. They also detected sharp shifts in the magnetic field direction, another hallmark of crossing from heliospheric space into interstellar space. Before these direct measurements, scientists had hypothesized the location and characteristics of the heliopause through indirect methods, using observations of energetic particles and electromagnetic waves. The Voyager's data confirmed many models, but also raised fresh questions about the heliosphere's shape, size, and interaction with the interstellar medium. Far from being a smooth boundary, the heliopause is influenced by the Sun's movement through the galaxy and the varying density of the local interstellar medium. Current models suggest the heliosphere is not a perfect sphere, but rather elongated, like a comet with a blunt bow shock facing the direction of the Sun's travel and a long tail trailing behind. As the Sun moves at around 20 kilometers per second relative to nearby stars, it effectively scoops up interstellar material, shaping the heliosphere into this complex asymmetrical bubble. At the heliopause, physical conditions undergo dramatic changes. The plasma, the electrically charged gas, inside the heliosphere is cooler and dominated by solar wind particles, while outside, in the interstellar medium, gases are hotter and sparse, with different magnetic field orientations. This boundary is thought to be a turbulent zone, where instabilities arise, mixing particles from both regions and creating complex magnetic reconnection events, similar in principle to phenomena observed on Earth in the magnetosphere. Understanding the heliopause also provides insight into stellar astrospheres more broadly, the analogous bubbles produced by other stars. These astrospheres influence the habitability of planets orbiting those stars by modulating their cosmic environments. Comparisons between the Sun's heliosphere and others throughout the galaxy help astronomers piece together a universal picture of how stars interact with their galactic surroundings. Interest in the heliopause extends beyond pure science. As humanity contemplates future interstellar missions, crossing the heliopause represents a profound milestone, a tangible step from a star's protective domain into the untamed cosmic sea. The Voyagers gave us a preview of this journey and continue to send back invaluable data from the interstellar frontier, even after more than 4 decades in space. In summary, the heliopause is the definitive boundary of our solar system, an invisible and dynamic frontier where the Sun's influence wanes and the galaxy's forces take over. This boundary protects us from the harshest cosmic radiation, shapes our space environment, and acts as a gateway to the mysteries that lie beyond. As we continue to explore and observe, the heliopause remains a focal point, the real edge of the solar system and the frontier of our interstellar voyage. From here, our path leads naturally to the brave spacecraft that have crossed this boundary, humanity's own messengers venturing further than any before. We will soon learn about their epic journeys and the treasures of knowledge they have brought back from the edge of the solar system and into the depths beyond, the outer planets and their moons. Voyager 1 and 2 sent back stunning images of Jupiter's swirling storms and intricate moon Io's volcanic eruptions, Saturn's majestic rings and Titan's thick atmosphere, Uranus' tilted magnetic field, and Neptune's dynamic weather systems. Their encounters expanded our knowledge of the solar system's complexity and diversity, opening new questions about planetary formation, atmospheres, and potential habitability. However, the scope of the Voyager missions did not end with the exploration of the giant planets. After their close encounters, both spacecraft were tasked with an ambitious extension to journey beyond the planets, through the distant fringes of the solar system's atmosphere, and into interstellar space itself. The transition from the planetary mission to the grand voyage into interstellar space required remarkable resilience from these probes. Power sources, instruments, and communication systems originally designed for a few years of operation have functioned for decades, defying expectations. Their nuclear-powered batteries, which slowly decay, have supplied enough energy to keep instruments and transmitters alive well past their planned lifetime. As the Voyagers ventured farther, they crossed the heliospheric boundaries, like the termination shock and later the heliopause, the ultimate limit of solar influence. Voyager 1 was the first human-made object to break through the heliopause in August 2012, approximately 121 astronomical units from the Sun. Soon after, Voyager 2 followed, crossing this boundary in November 2018. These milestones transformed humanity's relationship with the cosmos. Our probes had left the protective bubble of the Sun and entered the true void of interstellar space. The data transmitted by the Voyager probes in this region have been nothing short of revolutionary. They revealed that the density of particles beyond the heliopause increases markedly compared to within it. They showed how the magnetic field changes direction as the spacecraft move from solar influence into the interstellar medium, and they detected cosmic rays at energies impossible to observe within the heliosphere. Voyager data also shed light on the nature of the turbulent boundary regions, how the solar wind slows and twists before coming to peace with the interstellar environment. Scientists learned that the heliosphere is neither spherical nor uniform, but shaped by the Sun's movement through interstellar space and the properties of the surrounding galactic medium. Beyond the purely scientific achievements, each Voyager craft carries a deeply human element, a gold-plated audiovisual disc known as the Golden Record. This time capsule contains greetings in 55 languages, music from around the world, natural sounds of Earth, and images depicting humanity and our planet. It's a message in a bottle, an invitation extended to the stars in hope that some other intelligence might someday discover our existence beyond the solar bubble. Despite the enormous distance, Voyager 1 is over 14 billion miles from Earth as of the early 2020s. The spacecraft continued to communicate, albeit faintly, with NASA's Deep Space Network. Signals take over 20 hours to travel one way, and communication grows more challenging as power levels decline, but the mission team continues to operate and receive data for as long as possible. The legacy of the Voyager missions lies not only in their pioneering flights or groundbreaking scientific discoveries, but in their embodiment of human curiosity and ambition. They have extended our senses and presence far beyond what we once thought possible, sending us pictures and measurements from realms no one has before touched. Looking ahead, the Voyagers will continue sailing outward, carried inexorably by their initial momentum. Perhaps centuries from now, they might wander through new star systems, silent emissaries representing an early chapter of humanity's desire to explore the cosmos. As we reflect on these incredible journeys, our next exploration brings us deeper into what the Voyagers have revealed, the data and discoveries from the edge of our solar system, inviting us to unlock the mysteries of the space where the sun's domain gives way to the vast interstellar wilderness beyond. As we stand on the frontier of our solar system, gazing out into the vastness beyond, it is the data collected from these remote reaches that shapes our understanding of what truly lies at the boundary between our sun's influence and interstellar space. For decades, the only direct insights we've possessed have come from the intrepid Voyager spacecraft, whose journey into these mysterious regions has provided a wealth of knowledge about the dynamic and complex environment at the edge of our solar bubble. This section delves into the remarkable discoveries drawn from their instruments and from other sources, revealing the nature of this boundary zone and the environment that lies just beyond. Voyager 1's crossing of the heliopause in August 2012 marked a historic moment, as it became the first human-made object officially to enter interstellar space. Before that, in the preceding years, it had passed the termination shock and traversed the heliosheath, regions that together form the outer layers of the heliosphere, where the solar wind slows down and interacts with the galactic environment. Voyager 2 followed this path several years later, providing a complementary set of observations from a different direction. These precious datasets allow scientists to examine the structure and properties of the solar system's edge in unprecedented detail. One of the most significant findings from Voyager data is the realization that the boundary of the heliosphere, once thought to be relatively smooth and simple, is in fact highly dynamic and complex. The termination shock, for instance, where the supersonic solar wind abruptly slows down to subsonic speeds, was found to be located at varying distances, roughly between 80 to 100 astronomical units from the Sun, depending on solar activity and pressure from the interstellar medium. This variability signifies the heliosphere's sensitivity to external and internal forces and illustrates that the protective bubble surrounding our solar system is far from static. Between the termination shock and the heliopause lies the heliosheath, a turbulent expanse where the solar wind is compressed, heated, and deflected as it pushes back against the galactic environment. Voyager 1 and 2's instruments detected increased particle densities and magnetic field intensities in this zone, as well as complex plasma fluctuations. These turbulent conditions hint at a chaotic interface where solar and interstellar matter intermingle, giving rise to a rich array of physical processes. Crossing the heliopause was a dramatic leap into truly interstellar space. The Voyager probes observed a marked increase in cosmic ray intensity, a flood of highly energetic particles originating outside our solar system, which had previously been partially excluded by the heliosphere's protective shield. This surge in cosmic rays is crucial for understanding the radiation environment that future interstellar travelers might face. Additionally, the direction and strength of magnetic fields changed noticeably, signaling entry into a new domain dominated by the interstellar magnetic field rather than the Sun's influence. Beyond the heliopause, the density of plasma, ionized gas, slightly increased compared to the inside of the heliosphere, confirming theoretical predictions about the local interstellar medium. This plasma, along with neutral atoms and dust particles, forms the raw material through which stars like our Sun travel as they orbit the center of the Milky Way. The data from the Voyager missions revealed that the local interstellar environment is not perfectly uniform, but contains subtle variations in density and magnetic fields, underlining the patchwork nature of the space between stars. Another fascinating insight comes from observations of the energetic neutral atoms, ENAs, particles created when solar wind ions exchange charge with neutral atoms. These ENAs travel back toward the inner solar system and can be detected by specialized instruments aboard missions like NASA's Interstellar Boundary Explorer, IBEX, and the now completed Cassini spacecraft. IBEX, for example, has produced maps of the heliosphere's outer limits, revealing unexpected features like a mysterious ribbon of high ENA emissions encircling the heliosphere, challenging pre-existing models and hinting at complex magnetic interactions at the boundary. Together, Voyager and IBEX have painted a picture of the heliosphere as both a shield and a mediator, fending off much of the galactic environment while facilitating an intricate exchange of particles and fields. This nuance reshapes our understanding of how the solar system fits within its galactic neighborhood and influences the conditions that envelop us. Moreover, the interstellar boundary region is further complicated by the relative motion of our solar system through the galaxy, moving at roughly 20 kilometers per second relative to the local interstellar medium. This motion creates a bow wave, or possibly a bow shock, much like a ship moving through water, although recent observations suggest the bow shock may be weaker or absent, depending on local conditions. How the heliosphere navigates this interaction with the interstellar flow is still being studied, but it adds yet another layer of complexity to the boundary environment. The knowledge gleaned so far underscores a broader theme. Space at this frontier is not empty or inert, but a lively, ever-shifting realm filled with charged particles, broken magnetic fields, energetic cosmic radiation, and dynamic plasma flows. This environment plays a critical role in shielding our solar system, in accelerating cosmic rays, and in influencing the interstellar weather that flows through our galaxy. As we continue to rely on the fading signals of the Voyager spacecraft and integrate data from newer missions and observations, our grasp of the solar system's edge grows richer. Each measurement deepens our appreciation of the boundary's complexity and the nature of the galactic environment just beyond. Although Voyager is now so distant that communications grow increasingly tenuous and power supplies wane, its legacy of first-hand data will outlast many generations, forming a foundation upon which future explorations can build. Looking forward, researchers anticipate that new missions equipped with more advanced technologies may someday venture beyond the heliopause, perhaps deploying swarms of smaller probes or sensors to map the interstellar space in greater detail. Until then, the data from the edge remind us both of the vast frontier that awaits and the extraordinary feats we have achieved in reaching it. In our next steps, we will explore the nature of this frontier environment itself, the interstellar medium, the vast space and matter that fill the cosmos between the stars. This medium not only shapes our solar system's interaction with the galaxy, but also serves as the cradle and canvas for the formation and evolution of stars, planets, and ultimately life itself. Beyond the protective bubble of our sun's gravitational and magnetic grasp lies a realm vast and intriguing. The interstellar medium, the true substance of space between the stars. While the night sky appears as a vast emptiness punctuated by distant points of light, this image conceals a subtle and complex reality. Space is not an absolute void, but a diffuse mixture of gas, dust, cosmic rays, and magnetic fields that play a crucial role in the life cycles of stars and the evolution of galaxies. The interstellar medium, often abbreviated as ISM, fills the space between stellar systems within a galaxy and constitutes approximately 10 to 15% of the visible matter in our Milky Way. Although extremely tenuous compared to Earth's atmosphere, the ISM is far from empty. It can be thought of as a delicate cosmic fabric, weaving together the cycles of birth, death, and renewal of stars. Understanding what the ISM is made of, how it behaves, and how it interacts with stars and planets helps us comprehend not only the structure of our galaxy, but also the origins of everything from solar systems to the very elements that make up our own bodies. Fundamentally, the ISM is composed primarily of hydrogen gas, the simplest and most abundant element in the universe, accounting for roughly 90% of the ISM's atoms. Most of this hydrogen exists in an ionized or atomic state, individual protons and electrons, or single hydrogen atoms. But a significant portion is molecular hydrogen, H2, especially in denser, colder regions, where stars may eventually form. In addition to hydrogen, the ISM contains helium, which makes up about 10% of the remaining atoms, along with trace amounts of heavier elements such as carbon, oxygen, nitrogen, and metals forged in the hearts of earlier generations of stars. Embedded within this gaseous mixture is dust, microscopic particles of carbon compounds, silicates, iron, and ice-coated grains that are remnants of ancient stars or products of chemical reactions within molecular clouds. Though dust constitutes only around 1% of the ISM's mass, its presence has outsized effects. It absorbs and scatters starlight, influences the heating and cooling of the medium, and serves as the scaffolding around which molecules can form. The ISM also hosts cosmic rays, high-energy particles, mostly protons and atomic nuclei, accelerated to near-light speeds by supernova shock waves and other energetic phenomena. These cosmic rays permeate the galaxy and carry with them clues about astrophysical processes beyond the galactic neighborhood. Their interactions with the ISM can ionize gas, triggering complex chemistry and influencing the environment for future star formation. Magnetic fields thread throughout the ISM, invisible but powerful. These magnetic fields can shape the motion of charged particles, influence the collapse of gas clouds, and help regulate the overall dynamics of the galactic medium. Observations using polarized light and radio wave emissions confirm that interstellar magnetic fields have strength on the order of a few microgauss, extremely weak by everyday standards, but significant enough at the low densities of the ISM to affect its evolution. The ISM is not uniform. Rather, it exists in multiple phases distinguished by differences in temperature, density, and ionization state. The hot ionized medium is extremely tenuous and can reach temperatures of millions of degrees Kelvin, often found in cavities carved out by supernova explosions. The warm, neutral, and ionized mediums are somewhat denser and cooler, filling much of the galaxy's volume. Finally, cold molecular clouds, composed largely of molecular hydrogen and laced with dust, are the dense, frigid sites where new stars are born. Transitions between these phases are dynamic and ongoing, driven by energy input from stars via stellar winds, radiation, and supernovae, as well as by galactic dynamics like spiral density waves. The ISM, in this sense, is an ecosystem. Stars are born from dense molecular clouds, live their lives emitting energy and matter, and ultimately die, often violently, enriching and stirring the medium once again. This cosmic recycling loop connects everything from the smallest dust grains to the largest galactic structures. Importantly, the solar system itself resides within a small region of the ISM known as the local interstellar cloud, or the local fluff, a relatively warm, low-density cloud approximately 30 light-years across. This cloud, embedded within the larger local bubble, an even more tenuous and hotter cavity created by multiple ancient supernovae, forms the immediate cosmic environment through which our Sun moves. The properties of this local patch of the ISM influence the heliosphere's shape and size and affect cosmic ray penetration into the solar system. Studying the ISM not only involves distant telescopes observing light across the electromagnetic spectrum, from radio waves to X-rays, but also in situ measurements from spacecraft like the Voyager probes. These have revealed changes in particle densities, magnetic field directions, and radiation levels as they exit the heliosphere and enter the interstellar environs. Understanding the interstellar medium is essential because it's the stage upon which the drama of star formation unfolds. Within its coldest and densest regions, gravity can overcome internal pressures and magnetic forces to collapse clouds into protostars and eventually full-fledged stars surrounded by planetary systems. The chemical richness of the ISM, including complex organic molecules found in molecular clouds, adds tantalizing hints about the potential for life's chemical precursors to form long before planets emerge. In summary, far from being empty voids, the spaces between stars are filled with a dynamic, multi-phase mixture of gas, dust, cosmic rays, and magnetic fields that shape the life cycles of stars and the architecture of galaxies. The interstellar medium is both a cradle and a repository, a place of creative destruction where the materials of the cosmos are endlessly cycled, from the ashes of exploded stars to the bright birthplaces of new suns. As we prepare to venture deeper into the mysteries of what lies between the stars, we will next explore the detailed components of this cosmic sea, the particles and fields that fill it, and how they influence everything from the behavior of cosmic rays to the evolution of galactic magnetic structures. These intricate details help paint a fuller picture of the interstellar medium, revealing the subtle but profound influences that govern our place in the galaxy. As we journey deeper into the fabric of the interstellar medium, we come to understand that it is far from a silent void. Rather, the space between stars is a vast sea teeming with particles and invisible fields that dance through the cosmic expanse, shaping both the environment and the very processes that govern the life cycle of stars, planets, and galaxies. This sea is composed of three main constituents: interstellar gas, interstellar dust, and cosmic rays, each playing vital and intertwined roles within the galactic ecosystem. Interstellar gas makes up approximately 99% of the mass of the interstellar medium. Predominantly hydrogen, the most abundant element in the universe, the gas exists in several forms: ionized, atomic, and molecular, depending on its temperature, density, and radiation environment. Ionized gas, known as plasma, is composed of charged particles and is found in the hotter regions where starlight or shock waves from supernovae strip electrons from atoms. Atomic gas, where atoms remain neutral, populates warmer, less intense areas, while the densest and coldest pockets contain molecular gas, where atoms bond to form molecules like molecular hydrogen, H2, carbon monoxide, CO, and more complex compounds. The temperatures in these gaseous regions vary dramatically, ranging from a sweltering 1,000,000 degrees Kelvin in the hot ionized medium to just a few tens of degrees above absolute zero in molecular clouds. These cold molecular regions, cloaked in the darkness of interstellar dust, serve as stellar nurseries, the birthplaces of new stars. Within them, gravity slowly pulls gas and dust inward until nuclear fusion ignites a new star, continuing the cosmic cycle. Interspersed throughout the gas are tiny particles of interstellar dust, microscopic grains that, despite comprising just about 1% of the mass of the interstellar medium, wield considerable influence. These dust grains are primarily composed of silicates, carbon compounds, iron, and ices containing water and simple molecules. They are leftovers from previous generations of stars, including material expelled during supernova explosions or stellar winds. Though small, dust profoundly impacts how we perceive the cosmos. It scatters and absorbs starlight, causing the familiar phenomenon of interstellar extinction and reddening, the dimming and color shifting of distant starlight as it passes through dusty regions. Dust grains are also the sites where molecules can form by providing surfaces upon which atoms meet, interact, and bond. This chemistry includes the formation of complex organic molecules, which are considered precursors to the building blocks of life. Cosmic rays are another fundamental component of the interstellar sea. These are high-energy particles, mostly protons, and atomic nuclei accelerated close to the speed of light, injected into the interstellar medium primarily by shock waves from supernova explosions and energetic astrophysical phenomena. Cosmic rays diffuse throughout the galaxy, carrying vast amounts of energy and ionizing atoms in their path. Unlike the relatively gentle flow of interstellar gas and dust, cosmic rays possess the energy to penetrate dense molecular clouds and planetary atmospheres, influencing chemical processes and serving as a form of radiation that shapes planetary environments. The interaction of cosmic rays with magnetic fields in the interstellar medium confines their motions, effectively trapping them within the galaxy for millions of years. These charged particles create ionization and heating effects in the ISM, promoting chemical reactions and affecting the dynamics of star formation. For example, ionized gas influences magnetic field coupling and gas-cloud contraction processes. The interplay between gas, dust, and cosmic rays forms a delicate and dynamic balance that maintains the structure and evolution of the interstellar medium. The gas provides the bulk material. Dust catalyzes chemistry and modulates radiation. Cosmic rays energize and transform the environment through ionization and heating. Together, these ingredients compose a complex, ever-changing medium that is as essential to the galaxy as oceans are to planets. Magnetic fields permeate this mixture, threading through gas and dust alike. Though invisible to the eye, these fields guide the motion of charged particles, including cosmic rays, shape the collapse of gas clouds into stars, and influence the large-scale structure of the interstellar medium. The tangled web of gas, dust, cosmic rays, and magnetic fields exhibits turbulence, shocks, and waves, phenomena that sculpt the cosmic landscape and drive the galactic ecosystem. This sea of particles and fields is also what our solar system is immersed in as it hurtles through the galaxy. It interacts with the heliosphere, the sun's magnetic bubble, affecting its shape and size. For instance, the cosmic rays blocked or modulated by the heliosphere impact Earth's radiation environment, while the dust grains, some of which become meteoroids, occasionally enter our atmosphere, bearing material from distant corners of the galaxy. Our understanding of this interstellar sea has been significantly enhanced not only by remote astronomical observations across the electromagnetic spectrum, but also through direct measurements by spacecraft like the Voyager probes, which journeyed into this domain and sampled the nearby interstellar plasma, magnetic fields, and particle fluxes. These man-made explorers confirmed that the environment beyond the heliopause is indeed a complex sea of particles and fields, dynamically shaped by interactions on scales far beyond what was previously imagined. As we continue to explore, the knowledge of interstellar gas, dust, and cosmic rays enriches our grasp of stellar birth, galactic ecology, and the conditions that govern the space through which all stars, including our Sun, and their attendant planetary systems travel. This cosmic ocean, though diffuse by earthly comparisons, is profoundly influential, weaving together the past, present, and future of the Milky Way and the broader universe. Looking ahead, in our next exploration, we will delve deeper into the influence of magnetic fields within this interstellar environment. the hidden guardians and messengers that silently govern the movements of charged particles and shape the evolution of stars and galaxies alike. In the vast expanses between stars, where matter is scarce and the emptiness seemingly endless, one invisible force quietly shapes the cosmos: magnetic fields. These unseen guardians, extending across light years of space, play a crucial role in the structure, behavior, and evolution of the interstellar medium and the galaxy itself. Their presence helps orchestrate the cosmic symphony of gas, dust, and energetic particles. They influence star formation, govern the motion of charged particles, and act as carriers of information across the vastness of space. Magnetic fields in interstellar space are not like the simple magnets we encounter here on Earth. They are complex, dynamic, and woven into the very fabric of the galaxy. Though their strength is extraordinarily weak compared to everyday magnets, typically a few microgauss, a millionth of a gauss, compared to Earth's magnetic field of about half a gauss, their influence over the incredibly sparse and vast interstellar medium is profound. Where do these magnetic fields come from? Part of their origin lies in the primordial magnetic fields seated in the early universe, amplified and stretched by galactic rotation and turbulence throughout billions of years. Dynamo mechanisms within galaxies wind and strengthen these fields, much like stretching rubber bands, creating an organized but turbulent magnetic structure within the Milky Way's spiral arms and between its stars. These interstellar magnetic fields permeate through clouds of gas and dust, guiding the motions of charged particles, ions and electrons, through space. Since charged particles spiral around magnetic field lines, these fields effectively channel the movement of plasma, influence the propagation of cosmic rays, and determine where and how energetic particles travel. One of the most dramatic roles magnetic fields play is in star formation. Inside dense molecular clouds, gravity battles against internal pressure and magnetic forces. Magnetic fields thread through these clouds, supporting them against premature collapse by exerting magnetic pressure and tension. These fields can slow down the contraction of gas, regulate fragmentation within clouds, and influence the orientation of resulting protostellar disks. At the same time, magnetic fields can facilitate star birth. Through a process called magnetic reconnection, field lines twist, break, and violently reconnect, releasing energy that can heat and compress surrounding gas. In collapsing clouds, these phenomena can trigger waves and shock fronts that aid in concentrating matter to spur the formation of new stars and planetary systems. Beyond star-forming clouds, magnetic fields define the shape and boundary of the heliosphere, the protective magnetic bubble blown by our sun's solar wind. The interaction between the heliosphere and the interstellar magnetic field determines the size and structure of our solar system's shield against cosmic radiation. Voyager spacecraft measurements as they entered interstellar space revealed subtle changes in magnetic field orientation and strength, confirming the presence and significance of these cosmic fields. Magnetic fields also influence the propagation of cosmic rays across the galaxy. By guiding charged particles along their twisted, invisible lines, these fields trap cosmic rays within the Milky Way's magnetic halo for millions of years, affecting both the radiation environment and the chemical evolution of the interstellar medium. The irregularities and turbulence within these fields scatter cosmic rays, modulating their energy and distribution, which in turn impacts processes such as molecular cloud heating and ionization, critical to star formation. Detecting and mapping interstellar magnetic fields pose enormous challenges. Since magnetic fields themselves do not emit light, astronomers infer their presence through indirect observations. One method involves measuring the polarization of starlight and dust emission. As dust grains align perpendicularly to magnetic field lines, they preferentially absorb and emit light in certain orientations. Additionally, radio observations detect Zeeman splitting, the subtle energy level splitting of atoms induced by magnetic fields, and Faraday rotation, a twisting of polarized light caused by magnetic fields interacting with ionized gas. These techniques, combined with theoretical models and spacecraft data, allow scientists to piece together the magnetic landscape of our galactic neighborhood. On the grand scale, magnetic fields contribute to the maintenance of spiral arm structures in galaxies, influence gas dynamics at galactic centers, and potentially play roles in the formation of large-scale cosmic structures. They act as messengers, preserving records of past energetic events like supernovae and providing clues about the galactic ecosystem's evolving magnetic environment. In essence, magnetic fields serve as both guardians, protecting young stars and planetary atmospheres by modulating radiation, and messengers, conveying clues about processes occurring over millions of light-years. They link the microcosm of star formation with the macrocosm of galaxy evolution, and their interplay with particles and radiation shapes the cosmic environment in ways we are only beginning to grasp. As we explore beyond the heliopause and peer ever deeper into interstellar space, understanding these invisible forces becomes key to unlocking the broader mysteries of cosmic origins and evolution. Next, we will turn our gaze to the stellar neighborhood itself, mapping the array of nearby stars and star systems that populate our corner of the Milky Way, and define the context in which these magnetic fields and interstellar mediums exist. As we turn our gaze beyond the Sun and its immediate influence, we begin to define our place within the stellar neighborhood, the collection of stars and star systems closest to our own. This cosmic vicinity occupies a relatively small region of the Milky Way galaxy, but provides a rich and varied assortment of objects that help us understand not only the local galactic environment, but also the broader processes of star formation, planetary system development, and the potential for life beyond Earth. To envision the stellar neighborhood, imagine a sphere roughly 30 to 50 light-years in radius centered on our Sun. Within this sphere lie hundreds of stars, ranging from familiar types like our Sun, a G-type yellow dwarf, to others that are far less luminous, such as red dwarfs, white dwarfs, brown dwarfs, and even exotic stellar remnants. Unlike the dazzling stars that sparkle in the night sky, many of these neighbors are faint or invisible to the naked eye, yet they contribute significantly to the makeup of our local galaxy. Mapping the stellar neighborhood is a task that has both practical and profound significance. It helps us understand the immediate cosmic environment that our Sun is traveling through, influences the heliosphere's shape, and sets the stage for potential interstellar travel or communication. Precise knowledge of nearby stars, their distances, motions, and compositions also informs studies of stellar evolution and the prospects for exoplanets within habitable zones. Historically, cataloging stars near our Sun was challenging due to the difficulty in measuring distances and proper motions with accuracy. However, advances in technology and methodology transformed this field. The introduction of parallax measurements, where observations of a star's apparent shift against background stars from different positions in Earth's orbit provide distance estimates, marked a groundbreaking development. Modern astrometry missions like the European Space Agency's Hipparcos satellite and its successor Gaia have pushed these capabilities to unprecedented precision, mapping the positions and distances of millions of stars within our galaxy. Gaia, in particular, has revolutionized our understanding of the stellar neighborhood by providing detailed three-dimensional maps of stars out to thousands of light-years, including the immediate surroundings of the Sun. It measures positions, distances, motions, and brightness with incredible accuracy, revealing subtle stellar movements and new members of the local community previously undiscovered. Within approximately 30 light-years, the majority of stars are red dwarfs, small, cool, and long-lived stars far less luminous than the Sun. These red dwarfs dominate the stellar census due to their abundance and longevity. Alongside them, we find white dwarfs, the dense remnants of stars like the Sun that have exhausted their nuclear fuel, as well as several brown dwarfs, objects too massive to be planets yet too small to sustain hydrogen fusion in their cores. One intriguing aspect of mapping nearby stars is the discovery of multiple star systems. Rather than being solitary, many stars travel in pairs or groups, gravitationally bound in binary or higher-order systems. These complex relationships provide natural laboratories for studying stellar dynamics and the formation of planetary systems under varying gravitational conditions. Careful tracking of stars' motions, proper motion and radial velocity, allows astronomers to assess not only their current positions, but also their past trajectories and future encounters. Our solar neighborhood is not static. Stars move through space at different velocities and directions, occasionally passing relatively close to the Sun over cosmic timescales. Such close stellar encounters can have dramatic effects on the solar system's outer regions, influencing objects like comets in the distant Oort cloud, and possibly even triggering episodes of increased cometary activity. Mapping these dynamics has practical implications as we consider the future of interstellar exploration and potential destinations for robotic, or eventually, crewed missions. Understanding which stars are nearby and their characteristics helps prioritize targets for telescope observations and spacecraft journeys, especially in the search for exoplanets within habitable zones. In recent years, discoveries of exoplanets around nearby stars, including intriguing Earth-sized worlds orbiting red dwarfs, have intensified interest in our stellar neighbors. Stars such as Alpha Centauri, our closest star system, come into sharp focus not only as astronomical objects, but as potential gateways to other habitable worlds. Equally exciting are the identification and characterization of faint, elusive objects like rogue planets and brown dwarfs roaming the neighborhood unbound to any star, highlighting the diversity and dynamism of our local environment. Mapping the stellar neighborhood, therefore, is an ongoing voyage of discovery, combining precise measurements, new technologies, and ever-expanding data to reveal the intricate web of stars and worlds that surround us. It places the Sun's solitary brilliance in the context of a community, a neighborhood filled with variety, motion, and potential for life beyond our own star. As we move forward, we will focus on the closest of these neighbors, the Alpha Centauri system and Proxima Centauri, examining their characteristics, planetary companions, and what they might mean for humanity's quest beyond our solar cradle. As we peer into the depths of our cosmic neighborhood, the two stars that shine brightest in terms of proximity are Alpha Centauri and Proxima Centauri, our closest stellar neighbors. Nestled just over 4 light-years away, these stars form a remarkable system that has long captivated astronomers and dreamers alike, not only because of their nearness, but also due to the tantalizing potential they hold for understanding worlds beyond our own. Alpha Centauri is, in fact, a triple-star system composed of 3 distinct stars bound by gravity. The 2 primary stars, Alpha Centauri A and Alpha Centauri B, are Sun-like stars orbiting a common center. Alpha Centauri A is a G-type main sequence star, closely resembling our Sun in terms of size, brightness, and spectral characteristics. Its partner, Alpha Centauri B, is a slightly smaller K-type star, cooler and less luminous, but still similar to our home star. Together, these 2 stars orbit each other at an average distance about the size of our solar system. a dance completed every 80 years. The relationship is a delicate balance of gravitational forces, providing a stable environment for potential planetary companions. Orbiting even farther away is Proxima Centauri, a small and faint red dwarf star, the closest individual star to the Sun at just 4.24 light-years, slightly nearer than Alpha Centauri A and B. Proxima Centauri is much smaller and cooler than the Sun, emitting only a fraction of its light. Despite this, it has gained wide recognition for hosting exoplanets within its habitable zone, regions where conditions might allow liquid water to persist, a key ingredient for life as we know it. The discovery of Proxima Centauri b in 2016, a planet roughly Earth-sized orbiting within the star's habitable zone, sparked immense excitement. While this world is subjected to intense stellar flares and radiation, a common trait among red dwarfs, its existence points to the intriguing possibility that nearby stars could host planets with environments conducive to life. Further observations have hinted at additional planetary companions in the system, suggesting a dynamic and diverse planetary neighborhood. Alpha Centauri A and B themselves have been studied extensively for their potential to harbor exoplanets. However, the binary nature poses unique challenges. The gravitational interactions between the two stars create complex orbital dynamics that could affect planetary formation and orbital stability. While no confirmed planets have yet been detected around these stars, advances in observational techniques and missions continue to push the boundaries, holding out the tantalizing hope of eventual discovery. Beyond their scientific allure, the Alpha Centauri system has captured human imagination as the most plausible destination for interstellar travel. Concepts such as Project Starshot envision sending ultra-light nanocraft propelled by powerful lasers to reach these stars within a few decades. The goal is to finally glimpse the planets orbiting our nearest neighbors up close, providing unprecedented data about the environments and possibly even signs of life. Studying Alpha Centauri and Proxima Centauri enriches our understanding of star and planet formation in multi-star systems, the effects of stellar activity on planetary atmospheres, and the potential for life-bearing planets in diverse conditions. These stars exemplify the rich tapestry of objects in our local cosmic backyard, affirming that even the so-called empty spaces between stars are, in fact, vibrant with worlds and possibilities. As our telescopes and spacecraft refines their view and our technologies advance, the prospect of unlocking the secrets of our closest stellar neighbors grows ever more promising. From the warm glows of Alpha Centauri A and B to the flickering, energetic pulses of Proxima Centauri, these stars invite us to explore beyond the veil of our solar system, standing as gateways to the boundless universe beyond. In the quiet darkness beyond the radiant glow of nearby stars and well-lit planetary systems, there exist elusive cosmic wanderers, mysterious objects that defy simple classification and challenge our understanding of what it means to be a star or a planet. Among these intriguing inhabitants of our galactic neighborhood are brown dwarfs and rogue planets, often called the dark travelers, because they emit little to no visible light and drift silently through the vast interstellar abyss. These enigmatic bodies illuminate a hidden dimension of the universe and broaden our perspective on the diversity and complexity of celestial phenomena. Brown dwarfs occupy a curious position between the smallest stars and the largest planets. Sometimes described as failed stars, brown dwarfs possess masses roughly between 13 and 80 times that of Jupiter. This places them below the minimum mass required to sustain hydrogen fusion, the nuclear process that powers stars like our Sun, yet above that of typical planets. Because of this, brown dwarfs never ignite sustained hydrogen fusion, and thus do not shine steadily as stars do. However, early in their lives, some can briefly fuse deuterium or lithium, transient signs of stellar potential. Their lack of sustained fusion means brown dwarfs are much cooler and dimmer than most stars, emitting primarily in the infrared spectrum rather than visible light. This characteristic makes them challenging to detect with traditional telescopes, as they remain largely invisible amidst the brilliance of brighter stars. It was only with advances in infrared astronomy and dedicated surveys that brown dwarfs were confirmed as a distinct class of objects beginning in the mid-1990s. Brown dwarfs exist in vast numbers throughout the galaxy, including in our own local neighborhood. Their faint, cool nature makes them important subjects for studying atmospheric physics under extreme conditions. Their atmospheres often display complex chemical interactions, cloud formations, and weather patterns akin yet distinct from those on gas giant planets. These features provide natural laboratories for understanding low-temperature physics and bridging the gap between planetary and stellar science. Equally fascinating are rogue planets, planetary mass objects unbound to any star and wandering freely through interstellar space. Unlike planets orbiting stars, rogue planets drift alone, illuminated only faintly by residual heat from their formation or by distant starlight. Their origins are varied. Some may have formed in isolation, like brown dwarfs, while others could be planets ejected from their original solar systems during dynamic gravitational interactions. Detecting rogue planets is a formidable challenge due to their lack of stellar association and faint emissions. However, astronomers have identified a handful of candidates using methods such as gravitational microlensing, where the rogue planet's gravity briefly magnifies light from a more distant background star, and deep infrared surveys, which seek their faint thermal glow. Some rogue planets may even be relatively close to Earth, just a few dozen light-years away, yet remain hidden due to their stealthy darkness. The existence of these dark wanderers enriches our understanding of how planetary and stellar systems form and evolve. Brown dwarfs and rogue planets blur the classical boundaries between stars and planets and illustrate the chaotic processes that govern stellar nurseries and gravitational dynamics. They hint at a galaxy teeming with unseen bodies, a population that has yet to be fully catalogued or understood. Moreover, rogue planets present intriguing questions about the potential for life in the cosmos. While lacking direct energy from a star, some could retain internal heat sources, such as radioactive decay or residual formation heat, allowing for subsurface oceans or atmospheres that might, in theory, sustain microbial life. These dark travelers expand the realms in which astrobiologists search for life, reminding us that habitability may not be confined solely to planets orbiting stars. From a cosmic perspective, brown dwarfs and rogue planets are also waypoints for future exploration. Their proximity, in some cases, makes them attractive targets for next-generation telescopes and potential interstellar probes, which could unveil their composition, atmospheres, and even clues about their formation and histories. In conclusion, the brown dwarfs and rogue planets that drift through interstellar space are the silent wanderers of the galaxy's shadowy realms. They beckon us to look beyond the glare of stars and the confines of planetary orbits into the mysterious depths where celestial objects defy neat classification and challenge our imagination. In the chapters ahead, we will continue to explore these curious denizens of the interstellar medium and peer into the growing search for worlds orbiting distant stars, expanding our grasp of what lies beyond the solar system's glowing frontier. In the grand quest to understand the universe beyond our solar system, one of the most thrilling pursuits has been the search for exoplanets, planets orbiting stars other than our Sun. Among these countless possibilities, the nearby stars within our cosmic neighborhood hold special allure. Their relative proximity offers the best hope for detailed observations, potential direct imaging, and perhaps someday, for missions that reach toward these distant worlds. Exploring the search for exoplanets around nearby stars reveals remarkable advances, challenges, and the tantalizing possibility that habitable and even inhabited planets might exist just next door in the cosmic dark. The journey to discover exoplanets began in earnest in the early 1990s, with the first confirmed detection of planets orbiting a pulsar and subsequently a sun-like star. Over the past 3 decades, the pace of discovery has accelerated dramatically, thanks to dedicated exoplanet hunting missions like NASA's Kepler Space Telescope and its successor, the Transiting Exoplanet Survey Satellite, TSS. These missions and ground-based observatories have collectively identified thousands of exoplanets, painting a picture of a galaxy teeming with planets in countless forms and environments. When focusing on nearby stars, generally those within a few dozen light-years, the identification and study of exoplanets involve multiple detection methods and specialized instruments. Stellar proximity makes certain measurements more feasible, allowing astronomers to sift through the stellar noise with greater precision and aim for detailed characterization. One of the most productive methods for finding exoplanets around nearby stars is the radial velocity technique. This method detects tiny wobbles in a star's motion caused by the gravitational tug of an orbiting planet. For stars close enough, this wobble translates into measurable shifts in the star's spectral lines due to the Doppler effect. Precision instruments such as the High-Accuracy Radial Velocity Planet Searcher, HARPS, spectrograph have enabled the detection of planets as small as a few Earth masses orbiting nearby stars, including red dwarfs like Proxima Centauri. Another powerful method is the transit technique, where astronomers observe periodic dips in a star's brightness as a planet crosses in front of it, blocking a portion of the light. Space telescopes like TESS are specifically designed to monitor nearby, bright stars to identify such transits, ideal for discovering planets in Earth-like orbits. Transits also provide opportunities to analyze planetary atmospheres during the event, unlocking insights into their composition and potential habitability. Direct imaging, though challenging, has made strides in studying exoplanets around young, nearby stars, where planets are still hot and luminous from formation processes. Advanced instruments equipped with coronagraphs and star shades block out the overwhelming glare of the host stars, allowing exceptionally sensitive telescopes, both on the ground and in space, to capture reflected or emitted light from exoplanets. While direct imaging remains limited to a subset of massive and widely separated planets, it offers the unique promise of studying exoplanets more comprehensively. In recent years, the discovery of Earth-sized exoplanets in the habitable zones of nearby stars, especially red dwarfs, has galvanized scientific and public interest. These zones are regions around stars where temperatures might allow liquid water on a planet's surface, a fundamental prerequisite for life as we know it. Notably, Proxima Centauri b and planets orbiting the TRAPPIST-1 system exemplify these captivating finds, sparking discussions about atmospheric conditions, stellar activity, and the potential for life. The search for exoplanets around nearby stars is not without challenges. Variable stellar activity, including star spots and flares, especially from active red dwarfs, can mimic or obscure planetary signals. Moreover, the gravitational interplay in multi-star systems complicates orbital dynamics and detection efforts. However, new techniques, sophisticated data processing, and multi-wavelength observations are continuously improving the reliability of discoveries. Looking ahead, future missions such as the James Webb Space Telescope, the European Space Agency's Plato, and proposed observatories like LUVOIR and HABEX aim to refine our ability to detect and characterize exoplanets around the nearest stars. These instruments will potentially reveal atmospheric compositions, surface conditions, and biosignatures, chemical markers indicating possible life. Thus, the search for exoplanets around nearby stars stands at a thrilling frontier in astronomy, bridging the technological capabilities of today with dreams of tomorrow's interstellar voyages. Each discovery not only enriches our understanding of planetary systems, but also deepens the fundamental question that has propelled humanity for centuries. Are we alone in the universe? Next, we will explore the remarkable methods that enable these discoveries, delving into the ingenious techniques that reveal distant worlds from the faintest of signals in the stellar light. Exploring the cosmos for planets orbiting stars beyond our own has become one of the central quests of modern astronomy. As technology advances and our curiosity deepens, astronomers have developed ingenious methods to detect exoplanets, planets outside our solar system, even when these worlds are light years away, too distant to be seen directly with conventional telescopes. Particularly around nearby stars, these delicate techniques enable us to glimpse the presence of exoplanets, their characteristics, and sometimes even a hint of their atmospheres. In this section, we delve into the primary methods by which astronomers uncover these hidden worlds in the vastness of interstellar space. One of the most fruitful and widely used techniques is the transit method. This approach involves monitoring the brightness of a star over time to detect periodic dips caused when an orbiting planet passes directly between the star and the observer, partially blocking its light. These transits produce characteristic, subtle drops in brightness, allowing scientists not only to confirm the presence of a planet, but also to estimate its size based on how much starlight it obscures. Missions like NASA's Kepler and TESS, Transiting Exoplanet Survey satellite, have employed this method to find thousands of exoplanet candidates, many around stars relatively close to Earth. The transit method's strength lies in its ability to detect small, Earth-sized planets when they orbit relatively close to their stars, resulting in frequent and observable transits. However, its effectiveness depends on a favorable alignment. Planets must pass along our line of sight, which statistically occurs for only a small fraction of systems. Still, for nearby stars, this technique is invaluable in identifying promising targets for further study. Complementing the transit method is the radial velocity technique, sometimes called the Doppler spectroscopy method. This approach measures minute shifts in a star's spectrum as it moves toward or away from Earth under the gravitational influence of an orbiting planet. A star with planets does not remain stationary. Instead, it wobbles slightly around the system's center of mass. These wobbles cause spectral lines to shift due to the Doppler effect, enabling astronomers to infer the presence and mass of an unseen companion. Radial velocity measurements can confirm transiting planets and detect non-transiting ones, especially when the planets are relatively massive and orbit nearby stars. Direct imaging offers another approach, though far more challenging since planets are typically billions of times fainter than their parent stars. This method requires advanced instruments equipped with coronagraphs or star shades that block or reduce starlight, enabling telescopes to capture reflected or emitted light from exoplanets directly. Direct imaging mostly detects large, young, and hot planets orbiting far from their stars, especially around nearby systems. It opens avenues for studying planetary atmospheres and surface conditions in unprecedented detail. Astrometry, the precise measurement of a star's position in the sky, provides yet another pathway to exoplanet detection. A star's slight positional shift caused by orbiting planets can be detected by measuring changes in its position relative to background stars over time. Although challenging due to the minute scale of these displacements, space missions like the European Space Agency's Gaia have revolutionized astrometry, identifying stellar wobbles indicative of planetary companions around many stars. Gravitational microlensing emerges as a unique technique sensitive to planets around distant stars, but it also offers potential for finding rogue planets or planets around nearby stars. This method leverages the bending of light by a massive object, like a planet acting as a gravitational lens when it passes in front of a more distant star. The temporary brightening provides clues about the lensing object's mass and distance. Despite its brief and unpredictable events, microlensing has enabled the discovery of planets invisible to other methods. Each of these methods brings complementary strengths and limitations, and the most comprehensive understanding arises from combining multiple techniques. For example, planets detected via radial velocity and transits can have their densities calculated, revealing clues about composition. Spectroscopic studies during transits allow astronomers to probe atmospheric constituents like water vapor, methane, or oxygen, enhancing our grasp of possible habitability. Technology continues to push the boundaries of exoplanet detection. Extremely precise spectrographs, adaptive optic systems to correct for Earth's atmospheric distortion, and space telescopes optimized for infrared wavelengths extend our reach toward smaller, Earth-like worlds around nearby stars. Upcoming missions and instruments promise to further refine the search, enabling characterization of exoplanet climates, weather, and potential biosignatures. The detection of exoplanets around nearby stars is not only a scientific triumph, but a prelude to humanity's quest to explore beyond our solar system physically. Identifying and understanding these worlds sets the stage for future ventures, whether through advanced telescopes peering further into their atmospheres or eventual interstellar probes journeying across the cosmic gulf. Next, we will turn to the revelations gleaned from studies of exoplanet atmospheres, unlocking the stories their gaseous envelopes tell about their formation, evolution, and the tantalizing possibility of life far from Earth. As we venture beyond the mere detection of exoplanets and begin to unravel the mysteries cloaked within their atmospheres, a new chapter in our understanding of distant worlds unfolds. Exoplanet atmospheres are the veil through which we peer to learn about a planet's composition, climate, geology, and, intriguingly, the potential for habitability or even signs of life. Studying these delicate gaseous envelopes has transformed the search for other worlds from a census of planets into a profound exploration of their natures and stories. The atmosphere of a planet, though often thin when compared to the planet's bulk, wields immense influence over environmental conditions. It controls surface temperature, shields the surface from harmful radiation and cosmic rays, and shapes weather patterns. For exoplanets many light-years away, the atmospheric composition provides clues to their geological activity, chemical processes, and histories of formation and evolution. One of the primary ways scientists analyze exoplanet atmospheres is through transit spectroscopy, which exploits the moments when a planet passes in front of its host star. During such a transit, a tiny fraction of the star's light filters through the planet's atmospheric layers before reaching our telescopes. Molecules and atoms in the atmosphere absorb characteristic wavelengths of light, imprinting subtle signatures in the star's spectrum. By carefully measuring these absorption features across various wavelengths, from visible to infrared, astronomers infer the presence of gases such as water vapor, methane, carbon dioxide, oxygen, and exotic clouds or hazes. For example, hot Jupiters, giant gas-rich exoplanets orbiting close to their stars, have provided some of the earliest and clearest atmospheric data. Their bloated sizes and short orbital periods make them ideal candidates for spectral analysis. Observations have revealed atmospheres rich in sodium, potassium, and complex molecules, along with temperature inversions and dynamic weather patterns, including strong winds and condensate clouds. These insights have challenged and refined our models of planetary atmospheres under extreme conditions. Smaller and cooler worlds, including super-Earths and mini-Neptunes, hold particular interest because they may bridge the gap between gas giants and rocky planets like Earth. Detecting and interpreting atmospheres on these planets is more difficult due to their smaller sizes and thinner atmospheres, but ongoing technological advances and future missions promise improved capability. The James Webb Space Telescope, JWST for instance, is poised to probe atmospheric compositions of Earth-sized planets around nearby stars with precision unprecedented before. Beyond composition, atmospheric studies also provide clues about planetary habitability. The presence of water vapor is a key marker, as water is a universal solvent critical for life as we know it. Trace gases such as oxygen or methane, if found together out of chemical equilibrium, might indicate biological activity. Clouds and haze layers complicate observations but also play vital roles in climate regulation, albedo, reflectivity, and surface conditions. Exoplanet atmospheres also tell stories of planetary formation and evolution. For instance, detection of heavy elements or unusual molecules may suggest past atmospheric loss due to stellar winds, evidence of volcanic outgassing, or interactions with nearby bodies. Some planets exhibit inflated atmospheres being eroded by intense radiation, shedding layers into space. For rogue planets drifting through interstellar space, residual atmospheres or thick insulating layers might preserve internal heat, with implications for potential subsurface habitability. Studying atmospheric escape processes is equally critical. How a planet loses or retains its atmosphere shapes its long-term climate stability and potential to support life. Observations of hydrogen exospheres or helium tails have provided dramatic evidence of atmospheric erosion, often linked to the activity level of the host star. In addition to chemical composition, atmospheric dynamics, such as temperature gradients, wind speeds, and weather patterns, are beginning to be revealed through phase curve observations, where the brightness of a planet changes as it orbits, showing different sides to observers on Earth. These data open windows into climates unlike anything on Earth, illuminating exotic meteorology on distant worlds. Technological breakthroughs continue to push the frontier. Next-generation ground-based telescopes like the Extremely Large Telescope, ELT, and space missions equipped with advanced spectrometers will enable more detailed and diverse atmospheric characterizations. These will allow us to study terrestrial planets in habitable zones, detecting biosignatures or environmental markers essential for life. Ultimately, exoplanet atmosphere studies connect us profoundly to the question of life beyond Earth. Through them, we seek not only to understand alien climates and chemistry, but also to glimpse the conditions where life might exist elsewhere. They transform distant, faint dots of light into dynamic worlds with complex stories, broadening our cosmic perspective. Having explored what exoplanet atmospheres reveal, we now venture into the concept of the habitable zone itself, the sweet spot around stars, where conditions might allow life to flourish beyond our sun. This understanding forms a cornerstone in the search for life and the mapping of potentially life-bearing planets. The search for life beyond Earth has long guided humanity's exploration of the cosmos, inspiring us to look for places where conditions might be just right for life to emerge and thrive. Central to this quest is the concept of the habitable zone, often called the Goldilocks zone, a region around a star where the temperature allows liquid water to exist on a planet's surface, a fundamental requirement for all known life. Understanding the habitable zone around stars beyond our sun opens a window into where life could flourish elsewhere in the galaxy. and helps focus our efforts in the search for extraterrestrial life. At its core, the habitable zone depends on a delicate balance between a star's radiant energy and a planet's ability to absorb and retain that energy. If a planet lies too close to its star, high temperatures can boil away water, create thick atmospheres dominated by greenhouse gases, and reduce the chances of stable life. Too far, and the planet becomes a frozen world, with any water locked in ice and chemical reactions slowing to a near halt. Within the habitable zone, however, conditions can allow water to remain liquid, flowing in rivers, pooling in oceans, and participating in the complex chemistry necessary for life. The range of the habitable zone varies significantly with the star's type and luminosity. Our own Sun's habitable zone extends roughly from 0.95 to 1.67 astronomical units, AU, where 1 AU is the average distance from Earth to the Sun. Planets within this zone, such as Earth and potentially Mars, may maintain temperatures conducive to liquid water, depending on atmospheric composition and planetary characteristics. Around cooler, smaller stars, such as red dwarfs, the habitable zone is much closer in, sometimes just a few million kilometers from the star. This compact zone means planets orbit more rapidly, often becoming tidally locked, showing the same face to their star at all times. While tidal locking raises challenges, such as extreme temperature differences between day and night sides, atmospheric and oceanic circulation might mitigate harsh conditions, preserving habitable environments. Moreover, the boundaries of the habitable zone are not fixed and depend on many factors beyond distance. A planet's atmosphere, for example, can amplify or moderate conditions through greenhouse gases, like carbon dioxide and methane. Geological activity, magnetic fields, and planetary albedo, reflectivity, all play roles in stabilizing temperatures and protecting developing life from solar and cosmic radiation. Expanding the concept further, scientists also consider the possibility of subsurface habitability, notably within icy moons or planets where liquid water may exist beneath frozen surfaces, warmed by internal heat sources such as radioactive decay or tidal flexing. Worlds like Jupiter's moon Europa or Saturn's Enceladus within our solar system exemplify these ideas, prompting speculation about analogous environments around distant stars. Habitable zones also evolve over time. Stars, including the Sun, gradually change in brightness and activity, causing their habitable zones to shift outward. Planets may enter or leave these zones over billions of years, affecting the window of opportunity for life to develop and persist. Understanding these dynamic processes is essential for identifying worlds with sustained potential for habitability. The discovery of numerous exoplanets within habitable zones around nearby stars, such as Proxima Centauri b, planets in the TRAPPIST-1 system, and candidates around other M-dwarfs, has energized astronomers and astrobiologists alike. These finds provide prime targets for future atmospheric characterization, search for biosignatures, and possibly, one day, direct exploration via interstellar probes. As we refine models and extend observations, the habitable zone remains a vital framework, guiding our cosmic search for where life might flourish beyond our Sun. It underscores the profound connection between stellar characteristics, planetary environments, and the potential emergence of life, reminding us that our story is but one chapter in a galaxy of possibilities. From here, our journey leads us into the dense and dynamic regions known as interstellar clouds, cosmic nurseries where stars and planets are born, and where the cycle of cosmic creation continues anew. Interstellar clouds, often called molecular clouds or nebulae, are the magnificent nurseries where new stars and planetary systems come to life. These vast, dense accumulations of gas and dust float quietly within the interstellar medium, serving as the cosmic wombs from which stars ignite and seed their surroundings with the ingredients necessary for the formation of planets, and potentially for the emergence of life itself. Understanding these interstellar clouds reveals both the incredible complexity of galactic evolution and the profound connection linking all matter in the universe. The typical interstellar cloud spans dozens to hundreds of light years and is primarily composed of hydrogen molecules, along with helium and trace amounts of heavier elements and complex molecules. Compared to the exceedingly thin gas filling most of space, molecular clouds are rarefied by Earth standards, but remarkably dense for cosmic environments, offering temperatures just a few degrees above absolute zero. Cold enough for atoms to bond into molecules, and for dust grains to become coated with ices. These cool, dark conditions are essential for triggering the processes that lead to star formation. Within these clouds, gravity takes center stage. Over time, slight perturbations, whether from passing shock waves, magnetic instabilities, or the influence of nearby supernovae, cause regions of the clouds to collapse. As the gas collapses under its own gravity, it fragments into increasingly dense cores, each the seed of a future star. This contraction heats the collapsing material, and when the density and temperature at the core become high enough, nuclear fusion ignites, marking the birth of a new star. The entrained dust grains within molecular clouds are not merely cosmic debris. They serve as catalysts for chemical reactions and as building blocks for protoplanetary disks, the spinning disks of material that surround young stars and from which planets eventually coalesce. These disks contain gas and dust that agglomerate into planetesimals and, through complex interactions and accretion, grow into full-fledged planets and other small bodies. Observations of young stellar objects across the galaxy have revealed spectacular disks exhibiting gaps, rings, and other structures, signposts of ongoing planet formation. Interstellar clouds come in various forms, from sprawling giant molecular clouds containing millions of solar masses worth of material to smaller, more transient dark clouds and cometary globules. These variations influence the types of stars and planetary systems they birth, as well as the timescales over which these processes play out. Giant molecular clouds, such as the Orion Nebula, host clusters of forming stars across a range of masses, frequently shaping complex stellar neighborhoods through interactions and feedback processes. The dynamic interplay of radiation, stellar winds, and magnetic fields complicates the picture. Massive young stars in these regions emit intense ultraviolet radiation that ionizes nearby gas, carving out bubbles and shaping the cloud's structure. This feedback regulates star formation by compressing some regions to trigger new collapse while dispersing others. Such processes contribute to the recycling of matter and energy in the galaxy. Advanced telescopes operating at infrared and radio wavelengths, such as ALMA, Atacama Large Millimeter Submillimeter Array, pierce the dense, dusty veils concealing molecular clouds' interiors, revealing the intricate filaments and cores where star formation is actively underway. Here, astronomers have observed complex organic molecules, including some that are considered building blocks for life, highlighting the chemical richness inherited by nascent planetary systems. Studies of interstellar clouds not only illuminate star and planet formation, but also enrich our understanding of the galaxy's life cycle. The transformation of diffuse interstellar material into dense molecular clouds and back again via stellar evolution and supernovae is a continuous, large-scale cosmic dance fueling galactic evolution. This cosmic recycling ensures that material forged in ancient stars spreads and eventually coalesces into new generations of stars and planets. Closer to home, The remnants of past molecular clouds bear clues to the origins of our own solar system. Isotopic studies of meteorites and the composition of comets suggest that our early sun formed within such a dense molecular environment, inheriting the chemical legacy woven in these stellar nurseries. Looking toward the future, upcoming missions and next-generation telescopes promise to deepen our insights into molecular clouds and star formation. With ever-increasing resolution and sensitivity, astronomers hope to capture the earliest stages of planet formation, probe the physical conditions shaping different types of stars, and uncover the chemical pathways that may lead to life-bearing worlds. In essence, interstellar clouds are the cradles of creation within our galaxy. From their cold, dark depths emerge the stars that light the cosmos and the planets that could harbor life. As we continue our journey beyond the solar system, these stellar birthplaces remind us of the profound continuity and interconnectedness that span the universe, from the vastness of interstellar space to the fragile beauty of life itself. As our exploration unfolds, we will next turn to the dramatic remnants of dying stars, the supernova remnants, and their essential role in cosmic recycling, perpetuating this endless cycle of destruction and birth. In the grand tapestry of the cosmos, death yields new life in a spectacular and transformative process known as cosmic recycling. At the heart of this cycle lie supernovae, the explosive deaths of massive stars, whose remnants scatter enriched material across the galaxy, seeding the interstellar medium with the building blocks for the next generation of stars, planets, and potentially life itself. Understanding supernova remnants and their profound role in cosmic recycling unveils one of nature's most dramatic and vital symphonies, connecting the birth and death of stars across time and space. A supernova occurs when a star of sufficient mass, typically greater than 8 times our Sun, exhausts its nuclear fuel, leading to the catastrophic collapse of its core under gravity. This collapse triggers a titanic explosion that outshines entire galaxies briefly and blasts the star's outer layers into space at velocities reaching thousands of kilometers per second. What remains is either a neutron star or a black hole nestled at the core, with the outer layers forming a complex, expanding shell known as a supernova remnant. These supernova remnants are vast clouds of ionized gas, dust, and high-energy particles that can persist for tens of thousands of years. Examples include the famous Crab Nebula and Cassiopeia A, both located thousands of light-years from Earth and studied extensively across the electromagnetic spectrum. These remnants are not merely cosmic debris. They are active sites where shock waves compress and heat the interstellar medium, triggering new waves of chemical synthesis and star formation. One of the most important contributions of supernovae to cosmic recycling is their role in dispersing heavy elements, also called metals in astronomical terms, that are synthesized during the star's life and in the explosion itself. Elements like carbon, oxygen, nitrogen, iron, and many others essential to planet formation and biology are forged via nuclear fusion in stellar cores and in supernova nucleosynthesis. As the remnant expands, these materials enrich surrounding molecular clouds, enhancing their chemical complexity and providing the raw ingredients for forming rocky planets and organic molecules. The expanding shock fronts of supernova remnants also energize the interstellar medium, driving turbulence, compressing gas clouds, and sometimes triggering the collapse of regions within molecular clouds that will later birth new stars. This feedback mechanism regulates the rate of star formation and shapes the structure of the galaxy over millions of years, weaving a complex interplay between stellar death and rebirth. Beyond propagation of material, supernova remnants accelerate cosmic rays, high-energy particles traveling near the speed of light that permeate the galaxy. These cosmic rays influence the chemistry of interstellar clouds, contribute to atmospheric ionization on planets, and carry information about energetic processes occurring thousands of light-years away. Additionally, magnetic fields within supernova remnants become amplified and tangled, affecting the propagation of shocks and particles. Observations in radio, X-ray, and gamma-ray wavelengths probe these magnetic structures and reveal the mechanisms of particle acceleration and energy distribution. Closer to home, evidence of past nearby supernovae can be found in isotopic anomalies within Earth's geological record, indicating that the solar neighborhood has been, and continues to be, influenced by these stellar cataclysms. The ancient explosions may have affected Earth's climate and radiation environment, demonstrating the interconnectedness of cosmic and planetary evolution. Technological advancements, from space telescopes like Chandra and XMM Newton to ground-based radio and optical observatories, have enriched our understanding of the physical processes within supernova remnants, their composition, dynamics, and interactions with the galactic medium. These observations continue to refine models of stellar evolution, explosion mechanics, and galactic ecology. In conclusion, supernova remnants are not mere vestiges of destruction, but dynamic agents of creation, sustaining the cosmic cycle of death and rebirth. By dispersing heavy elements, shaping interstellar clouds, accelerating cosmic rays, and influencing galactic structure, they foster the conditions from which new stars and planets emerge. This continuous process of cosmic recycling is fundamental to the evolution of galaxies and to the existence of life-supporting worlds like our own. Next, we will explore the theoretical outskirts of our solar system's influence, the Oort cloud, and its role in delivering icy bodies that connect our solar system to the vast interstellar space beyond. As we extend our exploration beyond the familiar territories of stars, planets, and interstellar clouds, we encounter two of the universe's most profound mysteries: dark matter and dark energy. These unseen components dominate the cosmos, shaping its structure, evolution, and ultimate fate. Although invisible and elusive to direct detection, their influence is undeniable, presenting some of the most fascinating challenges in modern astrophysics and cosmology. Dark matter makes up approximately 27% of the universe's total mass energy content, a substantial portion far outweighing the normal or baryonic matter comprising stars, planets, and living beings, which accounts for only about 5%. Unlike ordinary matter, dark matter neither emits, absorbs, nor reflects light, rendering it completely invisible across the electromagnetic spectrum. Its presence is inferred by its gravitational effects on the motions of galaxies and galaxy clusters, as well as the bending of light, known as gravitational lensing, passing near massive objects. The early clues to dark matter came from observations in the 1930s, when astronomer Fritz Zwicky noticed that galaxy clusters were moving too rapidly to be held together by visible matter alone. Decades later, precise measurements of the rotation curves of individual galaxies revealed a similar anomaly. Stars on the outskirts orbit at unexpectedly high speeds, implying there is far more matter in galaxies than can be accounted for by anything we can see. The nature of dark matter remains a mystery. The leading candidates are hypothetical particles that interact via gravity, yet very weakly, or not at all, through electromagnetic or nuclear forces. Among these are WIMPs, weakly interacting massive particles, axions, and sterile neutrinos. Despite extensive experimental efforts, including underground detectors and particle accelerators, no direct evidence for these particles has yet emerged, making dark matter one of the most compelling unsolved enigmas in physics. Dark matter's role is pivotal. It acts as the cosmic scaffold on which normal matter accumulates, driving the formation of galaxies and larger-scale structures. cosmological simulations incorporating dark matter align closely with observed galactic distributions and the large-scale cosmic web of matter that threads the universe. Without it, the universe would look very different, unlikely to host the systems and environments necessary for stars and life as we know it. Yet even more enigmatic than dark matter is dark energy, constituting roughly 68% of the universe's total energy budget. Dark energy is a mysterious force causing the accelerated expansion of the universe, first definitively measured in the late 1990s through observations of distant Type Ia supernovae appearing dimmer than expected. It acts as a kind of anti-gravity, pushing galaxies apart at ever-increasing speeds and shaping the ultimate fate of all cosmic structures. The simplest explanation for dark energy is the cosmological constant, a concept introduced by Einstein as an intrinsic energy density of empty space, or the vacuum itself. However, its theoretical origin and extraordinarily small but non-zero value present profound theoretical puzzles, often called the cosmological constant problem. Alternative theories invoke dynamic fields, modifications of gravity, or exotic components that evolve over time. Together, dark matter and dark energy govern the expansion history and structure formation of the cosmos. Measurements from the cosmic microwave background radiation, baryon acoustic oscillations, and large-scale galaxy surveys continue to refine our picture of the universe, highlighting the importance yet mystery of these dark components. While these phenomena remain unseen, advanced observatories, such as the Dark Energy Survey, the Euclid Satellite, and the upcoming Vera C. Rubin Observatory, are probing their effects with ever-increasing precision, hoping to unlock their fundamental nature. The resolution of these mysteries will not only deepen our understanding of the universe's composition and evolution, but may also revolutionize physics. As we contemplate these unseen facets of cosmic reality, we circle back to our solar system's theoretical reaches, to the Oort cloud, where icy bodies and comets lie at the threshold of the Sun's domain and interstellar space. It is here, amid the edges of what we know, that the interplay between the visible and invisible cosmos continues to inspire discovery and wonder. Far beyond the orbit of Neptune, and even past the farthest recognized dwarf planets, lies a hypothetical and fascinating realm known as the Oort cloud. This vast, spherical shell of icy bodies is theorized to encompass our solar system at incredible distances, representing the theoretical outermost reaches of the Sun's gravitational influence. Though it remains unobserved directly, the Oort cloud is an essential piece in understanding the architecture, formation, and evolution of our cosmic neighborhood, acting as a reservoir of long-period comets and providing a bridge between the solar system and interstellar space. The concept of the Oort cloud was first proposed in 1950 by the Dutch astronomer Jan Hendrik Oort to explain the origins of comets with highly elongated orbits, comets that sometimes take tens of thousands or even millions of years to complete a single trip around the Sun. These so-called long-period comets exhibit trajectories indicating they come from a distant, spherical reservoir of icy objects far beyond the known planets. Estimated to reside somewhere between 2,000 and 100,000 astronomical units, AU, from the Sun, where 1 AU is the average Earth-Sun distance of about 150 million kilometers, the Oort cloud forms a spherical shell enveloping the solar system. At such vast distances, objects orbit the Sun so slowly and weakly that the gravity of passing stars and the tidal forces exerted by the galaxy itself can perturb their orbits, occasionally nudging some comets inward toward the Sun. The composition of the Oort cloud is believed to be primarily icy objects, remnants from the early solar system, consisting of frozen volatiles like water, methane, ammonia, and carbon dioxide. These remnants are leftovers from the primordial planetesimals that coalesced during the formation of the solar system, but were gravitationally ejected by the giant planets to distant orbits. Thus, the Oort cloud contains a fossilized record of the solar system's infancy and dynamic history. Despite its theoretical nature, the existence of the Oort cloud is widely accepted due to the consistent orbital characteristics of long-period comets and the absence of convincing alternative explanations. However, direct detection remains elusive, as the objects comprising the cloud are too small, cold, and distant to be observed with current telescopes. The Oort cloud serves as a crucial transition zone between the gravitational domain controlled by our Sun and the vast realm of interstellar space. Objects within it are only loosely bound to the Sun, making it sensitive to external perturbations, including passing stars, molecular clouds, and the galactic tidal field. These influences can send comets hurtling inward, providing a steady, if sporadic, stream of visitors to the inner solar system over millions of years. Understanding the Oort cloud is key for comprehending the interplay between the solar system and the broader galaxy, as interactions at its fringes represent the outer limits of solar influence. Its outer boundary marks where the Sun's gravity competes with the galactic environment, a frontier where the familiar gives way to the interstellar medium. Furthermore, the Oort cloud may hold clues to the early processes of planet formation and migration, illustrating how the giant planets shaped the primitive solar system. Studying the comets originating there also enhances our knowledge of prebiotic chemistry, since comets carry organic molecules that could have contributed to the origin of life on Earth. As technology advances, future telescopes and space missions may eventually glimpse the faint, distant objects of the Oort cloud or detect their cumulative effects, bringing direct observational evidence to bear on this theoretical realm. Having explored the theoretical outskirts of our Sun's reach, our journey now shifts inward again, focusing on comets and icy bodies, the messengers from this deep outer abyss that occasionally journey inward to illuminate the skies and deepen our understanding of the solar system's boundaries and history. As we journey from the theoretical confines of the Oort cloud inward toward the more familiar regions of our solar system, we encounter comets and icy bodies, enigmatic messengers that carry with them the whispered history of our cosmic origins. These small, often icy objects drift silently in the outer realms before venturing inward, their spectacular tails illuminating the night skies and offering us rare and precious glimpses into the primordial material from the solar system's earliest days. Comets are composed primarily of ice, dust, and organic compounds, remnants from the protoplanetary disk that surrounded the young Sun over 4 billion years ago. These ancient materials have remained relatively unchanged, frozen in the deep cold of space within reservoirs like the Kuiper Belt and the more distant Oort cloud. When their orbits bring them closer to the Sun, the increasing heat causes their ices to sublimate, transforming directly from solid to gas, creating the glowing coma and characteristic tails that streak across the sky. These tails, one laden with dust and the other with ionized gases, interact dynamically with solar radiation and the solar wind, forming the ethereal displays that have captured human imagination across cultures and centuries. What makes comets so fascinating to scientists is that they are essentially time capsules, preserving the chemical ingredients and physical conditions of the early solar system. The organic molecules detected in cometary comas include alcohols, hydrocarbons, and increasingly complex compounds, some of which are related to the building blocks of life. These discoveries fuel hypotheses that comets may have delivered vital prebiotic materials to Earth, possibly playing a significant role in the emergence of life. Beyond comets, there exists a population of icy bodies, often called trans-Neptunian objects, dwelling in the distant Kuiper belt that extends beyond Neptune's orbit. These bodies, like the dwarf planet Pluto and its kin, are composed of ice and rock and offer additional insights into early solar system dynamics and evolutionary pathways. The study of comets and icy bodies has been greatly advanced by space missions like ESA's Rosetta, which rendezvoused with Comet 67P Churyumov-Gerasimenko. Rosetta's detailed analyses revealed the comet's surface chemistry, complex morphology, and dynamic processes, revealing remarkable heterogeneity and complexity. These findings deepen our understanding of how such bodies evolve as they orbit the Sun and interact with their environment. Occasionally, these icy messengers venture beyond the heliosphere, interstellar space, or even originate from beyond our solar system. Their study helps bridge the gap between local celestial dynamics and the broader interstellar environment. Comets represent both literal and symbolic bridges, connecting the frozen outskirts of our solar system to the warmer, life-sustaining inner regions. Each passage inward illuminates the conditions and materials that led to the birth of planets and life itself, reminding us that the cosmos is a dynamic and interwoven system. With this understanding of comets and icy bodies as messengers from the outer abyss, we turn next to truly interstellar visitors, rare objects like Oumuamua and Borisov that defy easy classification and challenge our notions of cosmic boundaries. Their travels across the void offer unprecedented insights into the nature of the space beyond our solar system. Among the countless objects that traverse the vastness of space, a remarkable new class has captured scientific and public fascination: interstellar visitors, objects that originate beyond our solar system, journeying through the galaxy before briefly entering the neighborhood around our Sun. The first recognized examples, Oumuamua and Borisov, have challenged our understanding of cosmic dynamics and opened an extraordinary window into material from distant star systems, inviting us to contemplate the broader context of planetary formation and the nature of interstellar space. In October 2017, astronomers detected a fast-moving, cigar-shaped object racing through the inner solar system on an unusual hyperbolic trajectory, meaning it was not gravitationally bound to the Sun and thus from interstellar space. This object was named Oumuamua, a Hawaiian term meaning scout or messenger from afar. Its discovery instantly ignited excitement and debate. Unlike typical comets or asteroids in the solar system, Oumuamua exhibited extreme elongation, a shape unlike any comet or asteroid previously observed, and displayed non-gravitational acceleration that puzzled scientists. It lacked a visible coma, the characteristic gas and dust envelope of a comet, raising questions about its composition and origin. Theories about Oumuamua's nature ranged widely, from an unusual, elongated ice rock object to exotic explanations including icy debris or even artificial origin hypotheses. However, the data suggested it was a natural object expelled from another stellar system, having traveled for millions or billions of years through the interstellar medium before its brief passage near Earth. Its high velocity, some 87 kilometers per second relative to the Sun, and hyperbolic path confirmed its interstellar provenance. Only 2 years later, in August 2019, another interstellar visitor was detected, Comet 2Eotos-Borisov, named after its discoverer, Gennady Borisov. Unlike Oumuamua, Borisov resembled more traditional comets, exhibiting a bright coma and tail, and it followed a hyperbolic orbit indicating an origin beyond our solar system. Borisov's composition and outgassing behavior appeared similar to comets formed around our own Sun, offering a unique comparative study of cometary chemistry across star systems. Borisov's discovery reinforced the idea that interstellar objects may be more common than previously thought, passing through the solar system on rare but detectable occasions. Studying these visitors provides direct samples of material formed around other stars, dramatically broadening our understanding of planetary system formation and evolution beyond the solar system. Both Oumuamua and Borisov highlight the remarkable dynamic processes in the galaxy that can eject material from star systems to roam freely through the interstellar medium before possibly encountering other stars. Such interstellar wanderers act as cosmic ambassadors, carrying clues about their birth environments, chemical compositions, and the processes governing planetary system architecture across the Milky Way. Detecting and studying these fleeting objects pose enormous challenges due to their small size, great speed, and unpredictable trajectories. However, improvements in sky survey capabilities and dedicated efforts to monitor near-Earth space increase the prospects for discovering more interstellar visitors in the future. These objects also inspire profound philosophical reflections on cosmic interconnectedness and the possibility that material and potentially life-bearing molecules from one star system may seed or influence others. The study of interstellar visitors thus sits at the intersection of astronomy, planetary science, and astrobiology. As we continue on this cosmic journey, our next step takes us beyond our local neighborhood to examine the Milky Way itself, our vast galactic home, and our place within its sprawling and mesmerizing neighborhood of stars, gas, and dark matter. Through this broader lens, we contextualize not only these wandering visitors, but also the path that leads humanity toward the stars. Beyond the familiar glow of our sun and the distant twinkling stars lies the grander structure that cradles our entire solar system, the Milky Way galaxy. This sprawling, majestic spiral of stars, gas, dust, and dark matter situates us within a vast cosmic community, shaping our environment and influencing the very nature of space and time around us. Understanding the Milky Way and our place within its galactic neighborhood invites us to explore the broader context of our existence, revealing the intricate architecture of the universe on a grand scale. The Milky Way is a barred spiral galaxy, with sweeping arms full of stars and nebulae spiraling out from a dense, elongated central bar. It spans roughly 100,000 light-years in diameter and contains hundreds of billions of stars. Our solar system resides within one of its minor spiral arms, the Orion Arm, about 27,000 light-years from the galactic center. This position places us comfortably far from the chaotic center, avoiding the extreme radiation and gravitational disturbances near the supermassive black hole that lurks there, while still amidst a rich stellar environment. Our local region within the Orion Arm is studded with a variety of stars, stellar clusters, nebulae, and interstellar material. Nearby are several star-forming regions, such as the famous Orion Nebula, where new stars flare to life in giant clouds of gas and dust. The local stellar neighborhood is a dynamic community where stars orbit the galactic center in complex but orderly motions, bound by gravity but separated by vast distances measured in light years. The galaxy's structure is not limited to visible stars and gas. A significant portion of its mass consists of dark matter, an invisible substance whose nature remains elusive. This dark matter forms a massive spherical halo surrounding the Milky Way and governs the rotational dynamics of the galaxy, holding the stars and gas in their vast, graceful orbits. Movement within the galaxy is a cosmic dance. Our solar system orbits the galactic center approximately every 225 to 250 million years, traveling at about 828,000 kilometers per hour. This orbit carries us through regions of varying stellar density, gas clouds, and dark matter concentration, subtly influencing conditions within the solar system, including the likelihood of comet showers or nearby supernova. The Milky Way is also home to numerous satellite galaxies, smaller galaxies gravitationally bound and orbiting around it. Notable among these are the Large and Small Magellanic Clouds, visible from the southern hemisphere, as well as the Sagittarius dwarf galaxy, currently interacting and merging with the Milky Way. These interactions shape the galaxy's evolution, triggering starbursts and redistributing matter. Our understanding of the Milky Way has grown enormously through advances in observational astronomy, particularly with missions like the Gaia spacecraft, which has produced the most detailed three-dimensional map of our galaxy's stars to date. Such data reveal the structure, motions, and life history of the Milky Way with unprecedented clarity, providing insights into stellar populations, galactic formation, and the distribution of dark matter. Grasping our place within the Milky Way is not simply a matter of spatial coordinates. It influences the cosmic environment experienced by Earth and the solar system. The density of interstellar matter, the local radiation field, and the presence of neighbors, both stellar and substellar, contribute to shaping the space through which we travel. Looking outwards, we realize that the Milky Way is but one galaxy among billions in the universe, each with its own unique form and composition. Yet our home galaxy's spiral arms and rich history serve as an accessible laboratory for understanding galactic dynamics, stellar evolution, and the interplay between matter and forces on a monumental scale. As we truly appreciate our place within this vast and complex galactic neighborhood, our gaze naturally turns towards the prospect of venturing beyond, toward other stars and the uncharted territories that lie beyond the solar neighborhood. This journey, both literal and intellectual, prepares us for the next phase of exploration: the daunting and inspiring challenges of interstellar travel. The dream of journeying to the stars, the luminous points that have fascinated humanity since ancient times, has evolved from myth and imagination into a serious scientific and engineering challenge. As we contemplate the vast distances separating our solar system from even the nearest stars, the realities of interstellar travel come sharply into focus. Immense challenges of physics, propulsion, human endurance, and technology must be faced to make such voyages possible. Yet progress in theory and innovation suggests that, although daunting, interstellar travel could one day evolve from aspiration to reality. Understanding these concepts and their challenges provides a roadmap of humanity's next bold frontier. The central obstacle to interstellar travel is distance. The nearest star system, Alpha Centauri, lies about 4.24 light-years away, approximately 40 trillion kilometers. Even traveling at the highest speeds currently achievable by spacecraft within the solar system, it would take tens of thousands of years to arrive. Achieving travel times reasonable within human lifespans demands propulsion methods capable of reaching significant fractions of the speed of light, a formidable scientific and engineering feat. Several propulsion concepts have been proposed over the decades, each with its own advantages and challenges. Traditional chemical rockets, used extensively for space exploration to date, are wholly inadequate for interstellar journeys due to their limited energy density and exhaust velocity. One prominent idea is nuclear propulsion, using fission or fusion reactions to accelerate spacecraft to much higher speeds. Nuclear thermal rockets could provide greater thrust and efficiency than chemical propulsion, while nuclear pulse propulsion, concepts like the Project Orion, which envisioned detonating nuclear explosives behind a spacecraft, offered ambitious ways to reach a few % of light speed. Fusion-based designs, still theoretical, promise even greater potential, but remain experimentally unconfirmed. Laser propulsion, exemplified by concepts like Breakthrough Starshot, proposes propelling tiny, lightweight spacecraft mounted with large reflective sails using focused beams of powerful lasers from Earth or space. Theoretically, such probes could accelerate to 20% the speed of light, reaching Alpha Centauri in decades. This method reduces the need to carry fuel on board, but faces challenges in laser technology, sail materials, and maintaining beam alignment over immense distances. Other speculative methods involve antimatter propulsion, harnessing matter-antimatter annihilation to produce enormous energy densities, and theoretical concepts like the Alcubierre warp drive, which would involve bending space-time itself to achieve faster-than-light travel. While these remain far beyond current capabilities, they stimulate cutting-edge theoretical physics and inspire long-term thinking. Aside from propulsion, the challenges of interstellar travel include protecting spacecraft and potential passengers from cosmic radiation, micrometeoroid impacts, and extreme conditions over prolonged voyages. The effects of long-duration spaceflight on human biology, including psychological, physiological, and developmental aspects, pose profound questions that must be addressed in any crewed mission. Communication across interstellar distances also presents a challenge. Signals take years to travel between stars, necessitating autonomous spacecraft capable of independent decision-making and advanced onboard systems. Mission design considerations for interstellar probes involve trade-offs of payload mass, travel speed, energy requirements, and mission duration. Small robotic probes offer near-term feasibility with existing or near-future technology, serving as precursors to human exploration. Despite the daunting hurdles, incremental progress in propulsion technology, materials science, autonomous systems, and astrodynamics continually advances the feasibility of interstellar travel. Initiatives like breakthrough initiatives and growing international interest in deep space exploration reflect this evolving landscape. Beyond technical factors, the pursuit of interstellar travel raises philosophical and societal questions about humanity's place in the universe, resource allocation, and the motivations for venturing beyond our home star. As humanity stands at the threshold of moving from observation to journeying among the stars, the interstellar voyage symbolizes the enduring human spirit of exploration and discovery. The coming chapters in this saga will define not just where we might go, but who we are as seekers among the cosmos. In our next segment, we will explore the search for extraterrestrial intelligence. SETI, an endeavor that seeks to listen for signs of companions in the vast cosmic ocean, a complementary pursuit to physical interstellar exploration. Throughout human history, we have looked up at the stars and wondered whether we are alone in the cosmos. The profound question of whether intelligent life exists beyond Earth has inspired scientific endeavors, philosophical debates, and cultural fascination alike. The search for extraterrestrial intelligence, commonly known as SETI, represents humanity's focused and methodical effort to detect signals from technology-bearing civilizations elsewhere in the universe. This ambitious quest probes the vast darkness, listening carefully for hints of minds like our own, communicating across unimaginable distances. Founded as a scientific discipline in the mid-20th century, SETI began in earnest with pioneers like Frank Drake, whose famous Drake equation provided a framework to estimate the number of communicative extraterrestrial civilizations in our galaxy. This equation considers factors such as the rate of star formation, the fraction of stars with planetary systems, the fraction of planets that develop life, and the length of time civilizations emit detectable signals. While many parameters remain uncertain, the approach frames SETI as both an empirical and exploratory endeavor. The principal method of SETI has long involved the search for electromagnetic signals, particularly in the radio and optical ranges. Radio waves are favored because they travel vast distances with relatively little absorption or interference, and because they are technologically accessible to both potential transmitters and receivers. Arrays and large radio telescopes around the world scan the skies, analyzing rich data streams for patterns or anomalies that might indicate artificial rather than natural origins. Projects such as the Allen Telescope Array, the Arecibo Observatory before its unfortunate collapse, and international facilities have contributed thousands of hours of targeted and survey observations. Algorithms filter out the overwhelming background noise from stars, planets, pulsars, and human-made signals, hunting for narrowband transmissions, pulsed signals, or modulated patterns that would stand out as evidence of technology. In parallel, optical SETI searches look for brief flashes of laser light or unusual patterns of brightness that might represent intentional signaling. Advances in photodetectors and specialized telescopes have expanded the observational arsenal, offering new windows to detect possible interstellar communication. In recent years, innovative initiatives like Breakthrough Listen, backed by private philanthropy, have dramatically increased the scope and sensitivity of SETI efforts, deploying cutting-edge instrumentation and data analysis capabilities across multiple frequency bands. The goal is to survey millions of stars, millions of galaxies, and the entire sky faster and more thoroughly than ever. The search is not limited to passive listening. Some proposals suggest active SETI or messaging to extraterrestrial intelligence, METI, where humans broadcast deliberate messages into space, inviting responses. This approach, however, has sparked ethical and practical debates regarding risks and responsibilities in contacting unknown civilizations. SETI's challenges are immense. The signals must be distinct enough to rise above cosmic and terrestrial noise, and the timing must align. The transmitter must be sending when we are listening, a problem known as the needle in a cosmic haystack. There is also uncertainty about the types of technology or communication modes extraterrestrial civilizations might use, which could differ radically from human methods. Beyond searching for artificial signals, SETI endeavors often intersect with broader astrobiology, leveraging exoplanet discoveries and habitability studies to target promising star systems. Multidisciplinary collaborations enhance prospects by combining knowledge from astronomy, biology, anthropology, and information theory. While no confirmed detection has yet been made, the pursuit endures as a defining venture of human curiosity and scientific rigor. SETI embodies the hope that the vast expanse is inhabited by other intelligent beings, and that communication across the stars may someday unite us in understanding our place in the cosmos. As we consider the philosophical and existential implications of this search, we prepare to reflect on what it truly means to explore beyond our solar system, not merely as a physical journey, but as a profound quest for connection and knowledge at the edges of human experience. To contemplate exploring beyond the solar system is to engage not just with the scientific and technical challenges that lie ahead, but also with profound philosophical questions that touch upon the very essence of humanity, our place in the cosmos, and the nature of exploration itself. Venturing into the vast interstellar void is more than a physical journey. It is a symbolic and existential endeavor that challenges us to consider what it means to reach beyond the familiar, to seek connection in the unknown, and to confront the mysteries that bind us to the universe. At the heart of this reflection lies the recognition that exploration is inherently a human impulse, a drive to seek, to understand, and to transcend the boundaries imposed by our immediate environment. Since the dawn of our species, we have moved beyond caves to traverse mountains, oceans, and continents, propelled by curiosity, survival, and wonder. Extending this impulse into space and beyond the solar system represents a natural continuum of this urge, amplified by staggering scales of distance and time. Yet, interstellar exploration poses unique challenges to our traditional conceptions of journey and discovery. The immense distances mean that voyages could span generations, lifetimes far beyond current experience, necessitating profound societal commitment and perhaps new forms of existence. The possibility of never returning, of sending robotic emissaries whose operators remain on Earth, or of future generations stepping into the unknown, invites reflection on notions of identity, legacy, and the collective human spirit. Beyond practicalities, the act of exploring the stars prompts us to ponder our place in the cosmic context. Are we solitary sentinels adrift in a vast and indifferent void, or part of a grander community of life scattered among the stars? The search for extraterrestrial intelligence, the study of exoplanets, and the quest to physically reach other systems all feed into this inquiry, shaping how we understand life, consciousness, and meaning. There is also an ethical dimension to these endeavors. What responsibilities do we bear as we encounter potentially pristine worlds? How might contact with other intelligences challenge human values and beliefs? How do we balance the desire for exploration with preservation, caution with curiosity? Grappling with these questions requires wisdom and humility alongside ambition. Furthermore, interstellar exploration redefines our perspective on time and scale, compelling us to think beyond immediate gratification to longer-term visions that may outlast any individual or even civilization. It fosters a cosmic outlook that transcends national borders and short-term concerns, inspiring a sense of unity and shared destiny rooted in a common origin and journey. This philosophical reflection is not detached from the scientific. Rather, it enriches it. As technology advances and missions to the stars become more feasible, the human implications, the dreams, fears, hopes, and ethical choices must be integrated into how we chart our paths forward. In essence, exploring beyond the solar system is a profound expression of humanity's desire to understand itself and the universe. It challenges us to expand our horizons intellectually, spiritually, and morally, while daring to step into the unknown. From here, we prepare to speculate on future missions and imaginations. What next lies on humanity's quest to the stars? We explore both the promises and uncertainties that await as we boldly look outward and onward. As humanity stands at the dawn of a new era of cosmic exploration, the quest to journey beyond our solar system ignites visions of future missions and breathtaking possibilities. Driven by both curiosity and the innate desire to explore, scientists and engineers speculate on the technologies, strategies, and initiatives that might one day enable us to cross the interstellar void. This convergence of imagination, innovation, and determination carves a path toward realizing what once lived only in dreams, traveling to the stars themselves, and uncovering the mysteries that lie beyond our cosmic doorstep. Among the foremost concepts shaping future interstellar missions is the development of propulsion technologies capable of achieving unprecedented speeds. Projects like Breakthrough Starshot propose using powerful ground-based lasers to propel lightweight, sail-equipped nanoprobes to around 20% the speed of light. These probes could reach the nearest stars, such as Alpha Centauri, within a few decades, sending back invaluable scientific data about exoplanets and stellar environments. While the scale and time frame differ, this represents one of the few currently plausible methods to place a spacecraft beyond our solar neighborhood within a human timescale. Complementing the mission of tiny probes are ideas for larger, more complex spacecraft powered by nuclear fusion or antimatter engines. Though these technologies remain in experimental or theoretical stages, they promise tremendous thrust and efficiency, potentially allowing crewed or cargo missions over centuries or millennia. Advances in materials science, energy storage, and automation will be critical to making sustained interstellar voyages feasible. Robotic emissaries, equipped with artificial intelligence and autonomous decision-making, represent another frontier. Such machines might explore distant exoplanets, analyze their atmospheres, assess habitability, and even seek biosignatures or technosignatures, all without requiring real-time communication with Earth. These probes could establish the foundational knowledge needed before any human journey. On the scientific front, upcoming telescopes and observatories, including the James Webb Space Telescope and planned missions like the Large UV Optical Infrared Surveyor, LUVOIR, will revolutionize our ability to study exoplanet atmospheres, star systems, and galactic environments remotely. These instruments aid in identifying prime candidates for future exploration and deepening our understanding of the local interstellar medium and cosmic neighborhood. Beyond hardware and observation, conceptual studies also explore interstellar infrastructure, potential ways to establish way stations, resource extraction from asteroids or comets, and the use of relativistic communication networks. Harnessing in situ resources is a vital aspect of sustaining long-duration missions and expanding humanity's presence beyond Earth. Ethical and philosophical considerations increasingly influence mission planning. Decisions about which worlds to explore or potentially colonize, how to avoid contaminating other ecosystems, and managing the societal impact of such endeavors raise important questions. Responsible exploration calls for international cooperation, transparent policies, and a deep respect for potential extraterrestrial environments. Furthermore, the quest to the stars fuels a cultural and inspirational narrative vital to sustaining public interest and investment. It beckons humanity to unite in pursuit of knowledge and adventure, fostering education, innovation, and global collaboration. Looking even farther ahead, some scientists and visionaries contemplate technologies that transcend current physical limitations. Warp drives, wormholes, or other exotic physics concepts that could, in theory, allow faster-than-light travel. Though speculative today, continued research in fundamental physics might one day bring these ideas within reach. In sum, the future of humanity's quest beyond the solar system is a tapestry woven from scientific rigor, bold imagination, technological breakthroughs, and profound philosophical reflection. Every step forward, whether deploying nanoprobes to neighboring stars, deciphering distant atmospheres, or pioneering fusion propulsion, brings us closer to transforming our species from inhabitants of a solitary star system into interstellar explorers. As we prepare to face the ongoing mystery of what truly lies beyond the solar system, we carry with us the legacy of curiosity that has propelled us from the first steps on Earth to the vastness of space. Each discovery peels back the cosmic veil, inviting us deeper into the unknown and stirring the endless human desire to explore, understand, and journey ever onward into the stars. As we conclude our expansive journey exploring the vast realms beyond our solar system, we are reminded that, despite incredible advancements in technology and knowledge, the universe beyond remains a profound and enduring mystery. Our exploration has taken us to the theoretical borders of the Sun's influence, through the turbulent interface where the solar wind yields to the interstellar medium, and further into the cosmic neighborhood that stretches across countless light-years. Yet, with all we have learned, the fundamental question remains: what truly lies beyond the solar system? The boundaries of our solar domain, the heliopause and beyond, form a threshold between the known and the unknown, a boundary between a star's intimate environment and the larger galactic landscape. Space beyond these boundaries is sparsely populated by diffuse gas, dust, cosmic rays, and magnetic fields. But the true nature of this interstellar medium is only beginning to be unraveled. Our only direct emissaries to this frontier, the Voyager spacecraft, continue to transmit invaluable data, but their journey is slow and signals faint after decades of travel. We know that the interstellar medium is an active and dynamic expanse, home to clouds that birth new stars and planetary systems, threaded by magnetic fields that govern particle motions and cosmic rays that can permeate deep into planetary environments. Nearby star systems, each with their own planets, some possibly harboring life, dot this galactic neighborhood. The fabric of the Milky Way itself weaves these elements into a vast living organism, moving and evolving over eons. Yet much remains beyond even our most powerful telescopes and probes. The nature of dark matter and dark energy, comprising the dominant mass energy of the cosmos, remains hidden from direct detection, shaping the cosmic structure in ways we barely comprehend. The possibility of interstellar travelers, rogue planets and brown dwarfs wandering the darkness, and interstellar visitors passing transiently through our solar system appear tantalizing hints of a galaxy far more vibrant and alive than once imagined. The challenges of physically exploring these realms are monumental. Concepts for interstellar travel and the search for extraterrestrial intelligence embody both our highest aspirations and the limits of current science and technology. They invite us to expand our horizons in ways that test ingenuity, patience, and resolve. The ongoing mystery beyond our solar system is thus a reflection of the universe's vastness and our growing but still nascent capabilities as a spacefaring species. It is a call to humility and wonder, reminding us that each discovery only deepens the questions, that the journey of exploration is a continuous unfolding of horizons. As we stand on the threshold of this grand mystery, humanity's gaze lifts ever upward and outward, propelled by curiosity, imagination, and the enduring desire to know the cosmos. What truly lies beyond the solar system is not simply an answer waiting to be found, but a frontier inviting us to explore, wonder, and dream for generations to come.